Hello everybody, today we'll be doing number of islands given a m times n 2D binary grid, which represents a map of 1 being land and 0 being water. Return the number of islands. An island is surrounded by water and is formed by connecting adjacent land, horizontal or vertical. You may assume all 4 edges of the grid are all surrounded by water. Okay, let's take a look at this first example. In this first example, we have 1 island. Immediately, you would think the edge case would be 0 islands, and you wouldn't be wrong. There would be 0 islands, like so. There would be 0 islands in this very long island strip that we're viewing. So in this situation here, we have 3 islands, because we have 1 island here, 1 island here, and 1 island here. As you can see, this is pretty much a graph problem, and we can do this by DFS or BFS by expanding our islands and converting these items into 0 so that we don't encounter them a second time when we find the island. So basically, for m times n, we will start at every single spot, check if it's a 1. If it is a 1, then we would do a DFS or BFS to check all of its surrounding items to see if there's a 1 nearby, and if there is, go there and continue running BFS or DFS until it's no longer possible to find another 1, and then by converting it all to zeros or -1 something to notify that it's no longer an island, then we're good to go. However, there is a constraint that we would like to ask about, is it okay if we modify the grid? That is the question. And if it's not okay, then we can convert to -1 and then convert it back to 1 afterwards. That will take some time for space, or we could use space for time and then just create a deep copy of the grid and use that grid instead, and convert everything to 0. So if we're allowed to change the number of the grid and just return the number of islands we found, this makes this problem much easier, because it's just going to be the time complexity that we're looking at is going to be O of n, m times n. That's like the worst case, because m times m, and what's could times 2 at most, because let's just say we have a 1 that covers the entire board, right? Then we have visited every single spot. That's m times n. And we're gonna, after checking the first spot, we'll check all the other remaining spots. So that's m times n again. So that's m times n times 2, which is O of m times n. That's going to be the time complexity. The space complexity is going to be O of 1. The reason why it's O of 1 is because, well, we're not using any additional space other than keeping account of the number of islands. Maybe if we did, we are using recursion, whether we use recursion or BFS. If we use BFS, the maximum space we can use is like if we chose this particular spot and expand it into an island, it would be O of 4 spaces maximum, and then we would run through, well, actually, no, because that's a queue, and the queue can continue to expand as we push more and more things into it. So it's O of m times n if we use a queue. If we use a DFS call, I think it would be O of log m times m if we did DFS, because if we did DFS, we would go all the way through one path and then go all the way back and then try the next path. So therefore, it is going to be log m times m, because, not exactly, because can't we say, suppose we access all the items this way, then we try to access all the items down, and then try to access all of these items in the circle? I'm sure that's possible. So, okay, never mind. Space is m times n. Possibly. And let me write the reason down, because we check every spot and run DFS or BFS from each spot. So because DFS or BFS recursion could use up to O of m times n space. With that, I think we have completed our understanding what we're doing here, and we're ready to do the next step. If we understand the problem, then we must now match. The match is going to be a DFS or BFS. We can do both. And the plan, like we said, visits each location m times n, and then run BFS or DFS. For DFS or BFS, if the next location is 1, then continue. Otherwise, end. 1 being land. That's it. That's the plan. And let's implement. So let's get the m and n. So equals grid, length of grid, and length of grid at 0. So now we have m times n. So for I in range m, for j in range of n, we're going to look at grid, run a BFS, and increase if grid at m and n equals 1, then we're going to increase our count plus equals 1. We're going to start our count at 0. And after we set our count, we're going to run the BFS or DFS on this grid item. And that's it. And return the count. So let's create this BFS and DFS function. So define DFS. This is the easy one. And what we're going to take in is a coordinate. We're taking m and n. No, I and j. My bad. It's I and j. So what's going to happen is if I is less than, this is something that we want to have before DFS call, so we can have our m and n easily, or we could just do length of grid. I think this is confusing. Yeah, to say the least. So if it's less than 0, or I is greater than m minus 1, or, and let's put this into a parentheses as well. This makes it easier to read. Or j is less than 0, or j is greater than n minus 1, or this grid location at I and j is equal to 0, then let's quit. Otherwise, we see that it is a 1. So we're going to reset this grid item of I and j to be equal to 0. And we're going to run DFS on it. So I plus 1, j, DFS I minus 1, and j, DFS of I and j plus 1, and DFS of I and j minus 1. And after running all of this, we will be able to get the number of counts needed. So let's run DFS on I and j. And then we will return the count. Okay, let's see if our plan works out. I'm sure it does. Looks like we have an output of 0, so there needs to be some debugging that occurs. So there's not a point in which grid I and j equals 1 and increases the count, it seems. Yeah. That is weird. Oh, that's the reason. Because this is a string, not an integer. So the reason why it's an error, it's because it is an integer rather than a string. So let's run it again. Okay, it's been accepted. Let's run it against the edge cases and go from there. Let's click this, let's click that, and we have the edge cases. And we're looking good. Let's submit and see how we do. Perfect. We were able to complete this using a DFS call. And we did the review, and let's do the evaluation. Evaluate, and I think we were right on target with our earlier suggestion of m times n. And this was because of this for loop. You see m times n, and we did a DFS call, which has a max call of m times n, because we can only visit items that are 1 and continue visiting. Otherwise, we would stop visiting. As well as our space, because if the first item is a 1 and we keep on doing a depth first search, we would keep on going and generate the entire field of m times n in the memory stack. So that's going to be O of m times n because of recursion. Let's do a BFS since we have some time, and let's do that just for exercise. So we're gonna do the same thing, m times n, and we're gonna return if there's a grid, if it's outside the grid, or 0. And we're gonna set grid at I and j to equal 0. What is going on? And lastly, what we're gonna do here is run a BFS. So how is that gonna work? So Q Q is equal to the I and j, right? And we do a DQ on that, DQ, to do a pop left, make that easier. So while Q, we get an I and j from our items. So I and j equals to Q dot pop left. And we do this item here. So if this is not the case, then we'll not add it, continue, and otherwise we will set this item to 0 And then what happens here is that we will do a BFS call on, so we're going to add Q plus equals our I plus 1 j, I minus 1 j, I j plus 1, and I j minus 1. So add a bunch of items to the queue, and we will continue until we reach the point where there are no items left in the queue. So I think that should work. Let's try it and see what happens. Maybe there's some errors in there, maybe there aren't, but let's run BFS INJ. Okay, it looks good. And let's run the test cases. And we're looking good. Let's submit. And we're good to go. Looks like BFS saved us a lot of memory compared to DFS for some reason. That's was not to my prediction. I was thinking that DFS would save more space because we would reach a dead end and we would return that memory to the stack while we visit another link of items. Let me submit it one more time, just make sure that's not a fluke, that the memory usage is so low. It is not a fluke, and it is running pretty fast at this point. So let's run DFS again and see what's going on, and let's submit. And indeed, we are using more space, and we are running slower with DFS for some reason. I'm not too clear about the reason why DFS is slower. Maybe it has to do with the memory stack, or I think it maybe has to do with this queue append that is making things much faster. Well, with that, I hope you enjoyed this video. If you have a better way of us writing this code, please share. I think one of the better ways is to move these functions outside of our num islands and into our solution class as helper functions. That way, we don't have to have all this code in our way of looking at our most important code here. So one thing we can do is like set this as part of our class functions. So let's do that and move this out. So let's move this out and let's move this down here. And this way we can make this code a little bit more, let's run a self here. And this makes it a little bit easier to read. So self dot. And for the next person as well. So for this one, where's our DFS call? Hopefully everything's in line. Our DFS call is right here. Move it back, move back one more time. Move these back. Let's put a self here. And we'll run self.dfs. Oh, now the problem is that once we moved it out, we lost our reference of the grid that we had in scope. So this will not work. So we have to pass in the grid from now on, which is a little bit annoying. So this is what we'll have to do to sustain this. To make better code, we do have to. I mean, it's just by reference, so it's not going to cost any more memory. It's just a pointer to the grid. And so it is the cost of writing code that looks nicer to read. But I do think these functions are for this particular function and should sit inside this function, because otherwise people might like think that these functions are for some other usage, and they're not. They're for exactly only this purpose of working with this function. So I think sometimes when we're pursuing neat code, we forget the purpose of like scope, and just looking at it, it looks so nice, looks so clean. But in actuality, it is actually worse for the reader, because, well, I mean, we don't have that association that this is made for this particular function, num islands. Like, suppose our class becomes more and more complicated. What are these, like, it's best to move these functions into our num islands. So even though it looks a little bit worse, that's my thought on this. But this code does look a lot cleaner at this point in time, and if our class is this simple, it is best to write like this for this reason, for our circumstance. And with that, we have completed this problem. If you enjoyed this video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and I will see you in the next one. And be sure to comment below if you have, a solution you want to share, and let's all learn together. Thank you. Bye.